something to really look at and be aware of for both the examples I do today. And if you go back and look at the podcast, this is particularly important in yesterday's discussion. The question is what to do with the force of static friction. By now you should have the sense that one of two things happen. You're either in a situation where you solve for FF and compare to mu s Fn, asking the question, is it less than or equal to it? And if it is, then something happens, and if it's not, something else happens. That's one type of problem. The other type, okay, is you use the maximum value, which is FF equal to mu s Fn, to find something else. Now, how do you know when these are going to happen? Okay, one way to tell, for instance, is in this case, you might also have some unknown, say, pushing force. And if you looked at it and you did your Newton's laws, you would find that you don't have enough equations. You're one equation short to actually find the pushing force. You need to use the fact that the problem said, what is, say, the minimum force so that it just does not move? So you're going to take advantage of the maximum friction so that you use the minimum force, and that gives you your extra equation, the FF equals mu s Fn. The other type of equation is like the one you did yesterday in discussion section. Is the thing in static equilibrium? So there, you're solving for the force of friction that's required to achieve static equilibrium, because there are enough equations between the torque and the force equations to solve for it. The question says, is it in static equilibrium? That's asking you, is that force of friction less than or equal to the maximum it could be? If it is less than or equal to the maximum it can be, then yes, you can be in static equilibrium, because that force of friction is allowed. If static equilibrium requires a force of friction greater than the maximum, then you can't be in static equilibrium because you can't achieve that. It's bigger than the maximum allowed. And those are the two ways force of friction gets used. And if you look at the podcast I've added, I've really highlighted that in the last series of problems. So that was true in week 5 discussion on the ramp. You were distinguishing between these two type of friction problems, and that was true for yesterday's static equilibrium problem. So look at those podcasts. It's a really good way to see, if you compare those two problems, how we're using force of friction. And we're also going to see it today in our first problem with a ladder. So any questions on that? Yes? Yeah, that was just like an example that you might get in a problem, like some pushing force you need to find out. Yeah, I just threw that off to the side. That's not really part of those two sentences. Any other questions? So we have two main classic problems to do today. The first is a ladder. And the idea is, whether or not the ladder will stay up. So if this is my ladder, okay, you can imagine the ladder leaning against the wall and then trying to climb up my ladder. And at some point, it might slide, right? That's what you don't want to have happen. Now, this particular case, notice something about it, and it's something interesting. We actually have, where is it, a frictionless wall. And there is friction with the floor. So the very first question you might want to ask, and I want to go through this a little bit before I even ask my clicker questions and start to solve this problem. Is if I have a ladder resting against a wall and the floor, and I want to draw the free body diagram. Remember, in the discussion problem, if I have a beam with the wall and that is frictionless, is there any way for it to stay up? No. Why not? If the wall was frictionless, why can this beam not stay up? Well, we do have tension up in the rope and weight down, so we can get forces to balance. What ends up being a problem? Torque. And how is that easy to see that torque is a problem? Well, where would we take the torques about? A, B, or C? C. If I take the torques about C, how many torques do I have about point C? Just one, the weight, right? And so this thing rotates automatically. Now, let's look at our ladder. I say the wall is frictionless, but the floor has friction. I want you to draw an extended free body diagram for that ladder. Give you a hint. You should have 4 forces. Okay, anyone want to give me some forces to draw? Weight. Where does weight go? Down, and where physically do I put it? If that's A and that's B, where does weight get drawn? In the middle. Okay, it's still acting at L over 2. Okay, what else do I need to draw? What normal force? 2. From what and what? Okay, the wall normal force, which way does it go? To the right. And the floor, where does it go? Up. Okay, and what else do I draw? And which way does friction go? To the left. Why does it go to the left? Because the attempted motion is to the right. That's the direction it would slide. Now, is this enough to achieve static equilibrium? What would be some things we'd want to look at? Do I have enough forces that I can cancel all my forces in the x and y direction? Yes, because I've got one's to the left, one's to the right, one's up and one's down. Do I have enough torques that no matter what point I pick, I can cancel my torques? Probably. Okay, so if I pick point A, what happens torque-wise? Which way does weight go? Into the board or out of the board? Okay, go ahead and get your clickers out. And go ahead and vote. Is the weight around point A going into the board or out of the board? So we're doing the weight around point A. In or out of the board? 5 more seconds. 4, 3, 2, And 1. Good. Most of you got it. Okay? It's into the board. And these are the slightly trickier ones. We're kind of at an angle. But again, R is this way. So my fingers go down towards F, either this way or this way. And weight is down, so I have to curl my fingers this way to get FW, so it's going in. The other way I can think about it is the weight's going to pull down and swing it this way, which is into the board. Okay, what about FN2? Which way is that going to go? In or out? That one's going out. It's the other way. What about FF? That's also in. So I've got a couple in, couple out. I can cancel it out. And if you work your way through all of them, the torques can always cancel. We've got opposite forces at each point. Notice that was different, right? In this problem over here, the problem was our normal force was along the beam. It no longer helped us get a torque, right? Here, our normal force and our weight, if I consider point B, are pulling in opposite directions. And so they cancel each other out with a torque. So we're okay. Any questions on that? So let's go. Now we're going to solve the actual problem, right? So keep in mind what we had is our beam like that. And here's our wall, here's our floor, and here's our center of mass. So where do you want to compute the torques about when you solve this problem? The wall, the center of mass, the floor, it does not matter, but one of these will turn out to be better. It does not matter, and they're all exactly equal. Excellent. Most people went with what is, strictly speaking, the correct answer. Does not matter. It really doesn't matter in the sense that you will get the right answer using any of them. Every now and then, if you pick poorly, the force you really need as an unknown gets canceled out and the equation doesn't help you, but that's very rare. But usually, one of them does make the algebra shorter. And that's what I mean by one being better. Now, the other thing we want to think about before we start it, okay, is if I've got the floor, say I'm going to pick my point to be the floor, which is what I'm going to do for this problem, okay, which forces give us a non-zero torque? Weight, normal with the wall, contact with the floor, both A and B, all of the above. Okay, 5 more seconds. Everybody vote. Got everybody's vote in? Okay, good. Okay, this is kind of spread out. Now, we had a little bit of a peak at both A and B, but that's not even half the class. Okay, a lot of people went with just some of the others. I want you to figure this out. Talk with the people next to you. Why would it be just both A and B? Why not all of them? At a bunch with all of them? And why not just one of the others? Okay, very good. It's A and B. Now, why is it not the contact with the floor? Why not C? Because R is 0, right? Now, this is the first example problem we've had. So let's look at this one in some detail. Okay, again, the problem gave us the ladder's on the wall. It's half a meter away. There's some angle theta here. It's 2 meters up on the wall. The mass is 20 kilograms. Coefficient of static friction with the floor is 0.45. And the question is, does it stay? Well, we make our free body diagram, which we already did. So we have, I'm going to call that normal with the floor. We have force of friction. We have weight. And we have normal with the wall. We use our standard x and y, so z is out of the board. We set up our equations, and so we have our x forces. that's just the normal with the wall minus the force of friction equals 0. So we know that the normal of the wall equals the force of friction. We then have the y forces. That tells me the normal with the floor minus weight equals 0. So right there, we know that the normal with the floor equals 200 newtons, because that's the weight, which is mg. And then we did our torques about point A. Now, couple ways we can do this. Okay? That's angle theta. So from geometry, what's the angle in there? Theta, because that's the alternate interior lines. And the angle in here is 90 minus theta. Now, remember our torque, these are the first times they're not all at right angles. So the easiest way to make sure you don't make a mistake, I find, is to keep in mind what is, I didn't draw it really well. Let's see if I can get it better. Oh, I erased the entire line. There we go. There's that. There's FW. There's FW perpendicular. And there's F normal with the wall perpendicular. Right? That's the component we want, the perpendicular component. And so for both of these, we can now write for the weight, notice it's the sine of 90 minus theta that's giving me the perpendicular component because of this right there. We can't just put sine of theta because theta is defined to be this angle here, and it's not the correct angle between that force and R. And that's going to be an L over 2, and we're going to have minus the normal with the wall times, in this case it is sine of theta, times L equals 0. And again, we already did the in and out of the board and got the plus and minus signs. So that is our torque equation. Any quick questions on that? Let's pause there. Okay, remember the, we were told the length, I think. Yes. No, we weren't told the length. But L is the length of the board. Sorry. I had that in the earlier picture. I didn't put it in this one. So L over 2 is half that length. That's where the mass is, the center of mass. Any other questions? Yes?
Why is the weight negative again?
Okay, the weight, remember we're coming down from point A. So our fingers go from A up to where the weight is, and then we curl into the weight which is going down. And our thumb ends up out of the board. Right? Another way to think about it is about point A, the weight's going to rotate us this way. I curl my fingers the way it's rotating, and my thumb's out of the board. It's always a little tricky when the force, is the way that weight force is. The small angle makes it kind of want to somehow curl the other way psychologically. So remember, you can move that force down to point A. And that makes it clear you got to move your fingers down because it's pointing down. So you're always allowed to slide your force to where that point is. The easier one with torques is always check just which way will that force rotate it. Your intuition on which way something will rotate for a given force is usually very good. But you always want to compare that to doing it with the right-hand rule, because like I said, in 3B, you're going to use the right-hand rule for V cross B, where you'll have no intuition. So you just have to get really good at using the right-hand rule from these torque ones. Any other questions? So let me ask you this. Notice, I know the weight, right? So that's good. If I look at this equation, L is going to cancel out because over here is 0. So that's fine that I don't know L. I was able to solve for that, right? I don't know this, and I don't know this. And I also seem not to know theta. What am I going to do? I only have these two equations. Where do I get theta from? If you look in the problem, it's not given. Yes? I use the tangent. Notice I have a triangle over here. And this is why, once again, I say trig is the most important math in this class. Right? So the tangent of theta is 2 over 0.5, which tells you that theta is 76 degrees. And now I have enough to put everything together. If I take this equation, the normal with the wall, I put it all together, is 200 newtons times the sine of 14, that's the 90 minus 76, over the sine of 76, and that's going to equal 50 newtons. From that, if I use this equation up here, that tells me the force of friction is 50 newtons. And I wanted to check, right? Remember what I'm asking is, do I stay there? The question is the force of friction less than or equal to mu s Fn? That's my question. If this is greater than that, it can't occur, and I slide. If it's less than that, it can occur, and I stay. So I compare my 50 newtons to 0.45 times my 200 newtons. That's the force of normal with the floor. This multiplied out is 90 newtons, so it works. And I do not slide. I'm very safe on my ladder. Any questions on that? Yes?
For the force of friction, we're using the normal force from the floor because the friction is going to...
Because the friction is with the floor. Okay. Right. It's always the normal force that's the same contact as the friction that's the one that's relevant for setting the maximum friction. Any other questions? Yes?
How come you did a 2 for L over 2?
Where is it? I forgot to write it down as where it is. No, wait. Yeah, I think I just forgot to write it down. I think it goes here. So the force of friction, I can't remember now if I made this typo or I use this, so it's either 50 or 25. Both work. I will check that. My apologies. I don't know which typo I made in my notes. So I may have just forgot to write the 2 and I used it when I did the calculation. Or, good question. Any other mistakes that I made? Luckily, I still have my A. May not have my 100%, but I still have my A. Any other questions? Excellent. Now let me ask you this. Suppose I put a ladder against a wall with friction on a frictionless floor. Can it be in equilibrium? Now don't just guess. I want you to draw your free body diagram and then click in yes or no. Now for all of you who want to learn something that's applicable in your life, this is a really applicable one if you ever have to climb a ladder. In fact, years ago I had a student tell me that they got very excited because their dad was saying how they went, and the 66% of you got this right, realize that you can't do it on a frictionless surface. Their dad had put a ladder out on really wet grass and was surprised that it slid out from under him and he broke his arm. And her comment, instead of saying, "Oh, I'm sorry to hear that, Dad," was, "Oh, I learned why that happened in physics." Dad wasn't real happy. But let's look. What's the free body diagram? Give me the 4 forces. Come on. We have friction up against the wall. Normal force coming out this way. Weight down. And what do we have here at the floor? Normal force up. What's our problem? We have no what? I see people pointing. We have no force in this direction. There's only a force in that direction. The ladder has to move away from the wall. Now, as soon as you move away from the wall, what happens to the normal force and friction? They go to 0 because I don't have contact, and then all I've got is the weight pulling me down, and I fall down and break my arm. Okay? So notice how different this is from the other case. And so you really got to look at each situation carefully and see, am I balancing forces? Am I balancing torques? So you compare this to our sine. The sine had enough forces to stay up, but it didn't have the right torques, and so it fell. This, if you actually go through it, the torques look okay, but it's the force that's the problem. The whole thing gets pushed to the right. Any questions on that? Yeah. You got to look at both forces and torque to see if it's going to be in equilibrium. Now, let's go. So there was that one. We did some of those. Okay, let's go to our second problem. A 20 kilogram block rests at the end of a 5 kilogram beam of length L. The beam is supported by 2 supports. One is at the opposite end of the beam from the box. What is the minimum distance away from the opposite end that you can place the other support and still have the box balance? So basically what we're looking at, here is the standard one we did before, where you put the mass in the middle, and then they each get equal forces, and it holds and supports. Now what we want to do is kind of move this over. And obviously if I put the mass here, we're still good. But at some point, if I have the mass at the end, it flips up like it's doing here now. Okay? So I'm going to cheat a little bit because I don't have a long enough cart. Right? So here, I can put the mass at the end, and it's still kind of holding. It's not all the way at the end. But the question is, as I move this towards the middle, at what point is this going to flip up? That's what we're looking at. We're looking to see when that flips up. And the question we're going to ask ourselves first will be, what are the conditions for that? But before I ask the question or solve this, I wanted to make a quick note about drawing our extended free body diagrams. And I made this note in the solution. Right? If you notice, a lot of what we're doing is we have a beam, and we're either going to put stuff on it or hang stuff from it. So I might have a sign hung off over here and a box sitting on it there. If you want to be very careful, you should always draw three free body diagrams. One for this, one for the beam, and one for that. And what you'll see, right, the box has a normal force from the beam up and its weight down. This object here has some tension up and its weight down. And then the beam, since it's floating in air magically, has its weight down. Okay, this tension was up, so the matching tension is down. This normal force was up, so there is a normal force down. 95% of the time, the objects that are on your beam are simple like this and only have their weight as their other force. So both in the book and my solutions, you will often see us going straight to drawing the weight of the box down and not writing it like that, and going straight to the weight of this object down, let's call that object C, and not drawing the tension. So just be aware of that. It's a little dangerous. It doesn't always hold true, because you could imagine that this box was being pulled up with some rope. And now you have another force over here, and the force normal does not equal the weight. Okay? It equals some combination of the weight and what you're pulling with. So you do have to pay a little bit of attention when we're stacking objects on planks and stuff. If it's not the simplest of cases like this, you really want to draw each and every free body diagram. Most of your other free body diagrams, you won't be worrying about torques, because all the forces will be acting at just a single point. And it'll be just your main beam that you need to know where they're acting. Any questions on that? Pretty clear? So now let's go back to this and ask our first clicker question. It's the standard problem we have. We're always told something physical that's about to happen. In this case, we want a minimum distance between this support and here, so we know that that thing is going to balance. So I'm going to start moving this closer, and at some point this whole thing flips. And I'm solving for this distance. So what condition am I going to be looking for to get that distance? And it could be, so let's draw a little label so you guys have the same reference. Okay, here's my thing with the two supports. Here's my block at the end. Okay, and this is the support B that I'm moving around, and this is A that's at the end. So support A is that one. Support B is the one that I'm moving. And this distance X is what I'm looking for. The distance all the way to support B. So hopefully that helps you with your answer. Discuss this with your neighbor. This is a slightly tricky one perhaps. So let's make sure you get it right. Okay, most people got it correct, that it is both of these. Now the nice thing is, if you picked A or B, you'd still get the problem right? Because you could use either of those conditions to solve for the problem. So as long as you're not D or E, sorry you 11 people, you're not in trouble. But it is either of them. And one thing to notice, I don't know how many of you can't probably read the numbers, but 0 is straight up. So when it's in the middle, they both have force on them. Notice, as I move the block over, the dramatic thing is this one is starting to go to 0. Now, what does a normal force of 0 mean? No contact. What does it mean for the beam to flip? No contact. When is it going to just flip? When it just has no contact. So I'm going to move this over, and then it flips up when it hits 0. Now, it's got a little bit of, this thing isn't a point, it's a plane, so there's a little bit of a delay there. Now, the other thing, of course, to flip up, I need to rotate about point B. So I need some torques. And that's where point A, question A came in. A was talking about rotating about here. Answer B is talking about losing contact. Both of those are the condition for this to flip, and both of them happen at the same time. If you think about it, for this one to be true, right, if all I'm considering is the weight and the support, the weight of the beam, what I'm looking at is, here's the object, here's the weight of the beam. It's these two torques that are fighting each other, because this force goes to 0 right at contact, and I don't have it anymore. So really, the two work together. We good? Now, so there's that, both A and B. The other question, and hopefully you've seen it there in the visual now. Remember, this problem is about, here's support A, here's the block, and here's support B that I'm going to be moving all along here. And here's the center. Do I want B on this side of the center or this side of the center for this to work? Or do I need it right at the center of the beam? So I'm going to put the mass over here, and the question is, does this support end up this side of center, or right at the center of mass when I just flip? So do I end up over here, or right here at the center? And interesting, pretty big spread, but the actual answer is to the right of center. Okay? And yeah, I drew the picture correctly. Phew! I thought for a moment I'd drawn the picture backwards. Okay? For this to work, recall our free body diagram, right? We need the torques about this point to cancel each other out, which means I need a weight on this side to rotate it that way because the block is rotating it that way. If this support moves to this side of center, then the weight's over here, right? And both of my forces rotate it the same way, and it'll flip up. Because remember, it's going to flip when this normal force equals 0. So that won't be there to make any torque, right? So I need B far enough over to take advantage of the weight, or it's never going to balance. And I'm looking for the point where it just balances. Right? That's the, oh, okay. Yeah. Right? If we go back to the actual question, still have the box just balance. How far, or no, what's the minimum distance away, and it will still balance. So again, it's this point where it's just going to fall, or just be balanced. Notice, just be balanced or just fall are the same question in physics. We're going to set something equal to 0. Questions on that? So let's look at the solution to this problem. So what we have is our beam. We have point A. We have support B. The beam has some length L. And we're sticking a 20 kilogram block on the end. And the beam has a mass of 5 kilograms. And we want to solve for x. And we want sort of the minimum x, or how do we want to say it? We actually want kind of that maximum x, how far away we can get, and it still is stable. So as with everything, we're doing static equilibrium. We need our x, we need our y, we need our z out of the board. We're going to draw our free body diagram. We have FA up. We have the F from point B up. We have the box coming down. We have the weight coming down. The weight's at L over 2. This is at x. In the y direction, forces in the y direction, we get FA plus FB minus FW minus F of the box equals 0. If we're going to take our torques, we're going to take them about point B. And we know that FA is equal 0 when we're just about to fall. So we're not going to worry about that. We have the weight. And the weight about point B, notice its distance is x minus L over 2. And it's positive because from point B, our fingers go this way and we curl down into the weight and we come out. The box is going to go this way, curl into the box and go in, so it'll be negative. So that's the weight. We minus the box. And the way I drew it, the box is at L minus x, that distance from here, because the total length is L. We set that equal to 0. Now, if you go back to the problem, oh wait, nope, sorry. Oh, that's right. In this case, notice I didn't give you L. And if I work this out from the torque equation, okay, you're going to get x equals L times the weight over 2 plus the box divided by the weight plus the box. And this will come out to 0.9 times L. This is another thing. I did this on purpose. This is another thing that will happen in a physics problem. Every now and then, you give me the answer in terms of some variable you get to define. This is what we call a general problem. This will be true no matter what the length is. If you want to figure out where to put the other support, it's at 0.9 times that length. So you found a formula for the answer. And a lot of the equilibrium problems, this is the way it behaves. So you want to watch for that. If they don't give you the length, that's probably what you're going to do. Yes?
The second line where you have the torque,
B. That's a B. That's a really bad B.